everyone, and welcome to our, yes, it's the fifth virtual IAA lecture of the 2020-21 season. I was looking just outside the house earlier on, about 5 or so. There was a lovely crescent moon with Saturn and Jupiter, just 2-3 degrees apart, and 10 degrees from the moon. It looked very nice. If it's clear tomorrow, there'll be a similar thing. There'll be in a right angle formation, although obviously the moon will be a bit bigger. A couple of other similar related things. I was looking at one of the magazines. The lunar X and V, the clair obscure effects, I think they're called, should be visible on Sunday, coming to a climax about 2 p.m. It's daylight viewing. It would be worth having a look at. And later on the same evening, high magnification on Alba Tegnius, you would see a similar, well, not a similar, but another clair obscure effect, the face in Alba Tegnius. So that'd be 2 interesting things to have a go at. And of course, our webmaster, Paul Evans, will be putting his excellent December sky guide on our website on or around the 2nd of December. Lastly, 2nd of December is, of course, our next meeting date, and we will have Katrina Jackman from DIAS in the south with a talk, Adventures in the Outer Solar System. Okay, now to come on to our guest tonight, Dr. Jorick Vink, pardon me, who, if you're not familiar with Jorick, he started his career at Utrecht University in the Netherlands and had an 8-month stint at NASA's Goddard Space Center. After obtaining his PhD, he moved to ICL in London before coming to Armagh Observatory in 2007. He was acting director at the planetarium during the merger of the two organizations in 15-16. He obtained a visiting professorship from the University of Leeds in 2017 and is currently president of the IAU Commission of Massive Stars. Does that refer to yourself, the objects? And principal investigator, PI, of a large program with ESO VLT, complementing the Hubble Space Telescope HST ULLYSES project of massive stars. It doesn't seem possible, but Dr. Vink spoke last to us in February 2010 on a similar subject. I thought it was not as far back as that, but there you go.
A few times, I think.
Yeah. His talk tonight is entitled 30 Years of Hubble, Opening the Treasure Chest, which will be about the Hubble Space Telescope and the imaging therein. Lastly, as before, could I ask you to post any questions during the talk by using the chat button? We can refer to them when Dr. Vink has finished. Okay, thank you. Over to you, Dr. Vink.
Thank you, Danny. So let me just start about this this beautiful image. This is the image that Hubble released for its 30th anniversary. So these are 2 nebulae in the Large Magellanic Cloud, nearby galaxy, about 150,000 light years from the Milky, from us. This upper one, this big one, is like a star forming region with lots of massive stars that are ionizing this, lighting up this beautiful region. And then when the stars evolve, they become Wolf-Rayet stars. They become very, very hot. And then you see another region here that that has this Wolf-Rayet star here, and that has ejected all this mass, and that is also lit up by the Wolf-Rayet star. So this is material that's been ejected by the star, and that such material can then subsequently be used again for a new phase of star formation. So to me, this is a beautiful image, and it really captures a lot of my interest in star formation, massive stars, and pretty pictures. So when I was thinking about Hubble, I was thinking it's pretty amazing that that we've had all these beautiful images from Hubble, and I was sort of wondering, what are the scientific breakthroughs that we've had with Hubble? Obviously, in the last 30 years, we've made many breakthroughs in astronomy, and I think there is not a single field in astronomy where Hubble hasn't contributed. But there are certain questions, I think, that have been well, either resolved or massive progress been made, in particular because of its amazing capabilities. So I'm sure you're all aware that this is quite a large telescope. It's a 2.5 meter mirror that is maybe not particularly large anymore by today's standards compared to ground-based telescopes. But this was 30 years ago a pretty large telescope. But of course, the big improvement compared to telescopes on Earth is that you can see, you don't have the atmosphere, the Earth atmosphere in the way, so you can actually also look at the ultraviolet part of the spectrum, which you would not be able to see from Earth. And in fact, this telescope has the capability to see over an entire part of the electromagnetic spectrum, from the ultraviolet, the optical, to the infrared. So that makes this telescope quite unique. And it also had lots of surfacing missions. Now, the first one was a bit unfortunate. I'm sure you're all aware that when it was launched in 1990, that the mirror wasn't quite correct. So the first surface mission was, one massive task was to correct the mirror. But after that, the images were absolutely amazing. And I say images. Now, obviously, images are one main mode of observations for astronomers, and another one is spectroscopy. And there are other techniques, but I would still say that both imaging and photometry and spectroscopy are the two main workhorses of astronomical observations. And this telescope can do both. And it has had lots of updates of new instruments. And that means that even though this is a 30-year-old satellite, the instruments are actually much newer and they're very sensitive. And I'll come back to that at the end of the talk, because that's important for the large program that we are now looking at to do with the ULLYSES project. So when I think about Hubble images, to me, the main pictures that spring to mind are these beautiful images of planetary nebula. This is the Cat's Eye Nebula. But there are there's a whole, I'm sure you've all seen all these beautiful photographs of planetary nebulae. And the first thing that I think, even before you start talking about the science, is just imagining how beautiful it is. And it reminds me of a comment by Richard Feynman, the famous physicist from the Feynman diagrams. He talked about an artist friend who said, if you are doing all this science, then you take away all the beauty, because when I see a flower, I can just enjoy the flower. And then Feynman said, yes, but I can also see the beauty of the flower, but I have all kinds of additional questions about this flower. Why is it colorful? Can the bees see color? And all kinds of interesting questions. So he said to his friend, like, I see the same beauty as you see, but I think asking these scientific questions only adds beauty to that picture itself. And I think it's the same with astronomy. You have these amazing pictures, but the science it adds to the beauty. Now, planetary nebulae, like here, you can see, beautiful spherical structures, but you can also see aspherical structures. So this raises all kinds of questions about whether these stars are rotating, or if they have magnetic fields, or that maybe in the center there's a binary that distorts the system, and therefore this thing might be wobbling and creating all these amazing images. Now, my own field is that of stellar evolution, not so much of these low mass stars, but more the massive stars. Here is a simplistic picture of the two major evolutionary phases of both low mass stars like the sun and high mass stars. So for low mass stars, you form your stars out of these nebulae that I showed in the beginning, and you have your yellowish 6,000 degree surface, yellowish star that then expands, cools down to about 3,000 degrees, and then ejects this planetary nebula. And in the middle, you have just a white dwarf, which is basically the mass of a star in the size of the Earth. So it has a very strong gravity field. And the other one, the massive stars that I'm particularly interested in, they are, say, 20 or 100 solar masses. And they're blue because they're hotter. They're 40,000, 50,000, sometimes even degrees at the surface. And they also become red supergiants. And then they expel the outer layers in a supernova, at least for stars of order 20, 30 solar masses. They then make neutron stars where you collapse the size, well, the mass of a star into not the size of the Earth, but the size of a city like Belfast. And then you have extremely strong gravity. And then for the most massive stars, we think they actually skip the supernova stage. But the most massive stars basically remain blue, actually. They never become red supergiants. They remain blue, and they just directly collapse into a black hole. And of course, here the gravity is enormous. You just have a singularity. Now, these evolutionary phases of both high and low mass stars we have made a lot of progress in the last 30 years. But I wouldn't immediately say that Hubble, although Hubble has contributed many, many different questions in a lot of these areas of the stellar evolution, I wouldn't at this point in time say that Hubble has been the only or the main contributor to these fields. I think there are a couple of other fields in astronomy where that basically would not have happened if Hubble hadn't existed. And those are a few things that I want to specifically highlight. And maybe you all know, but maybe there are certain aspects that you are less aware of. So I thought it would be interesting to have a look at that. So the key areas that I wanted to look at are star and planet formation, cosmology, and then at the end I will also want to say something about this ULLYSES project. So let's start with star formation. Now, this is probably the most massive cluster in our own Milky Way. It has this NGC number 3603. This is called the New General Catalogue. That is actually a catalogue that was made in Armagh by Dreyer 100 years ago. And what you can see in this particular case is massive stars that are very hot and that ionize the interstellar medium, the medium around the stars, and they erode these pillars of creation. So I probably gave a couple of talks in the last couple of years, and I am sure I would have shown this picture because this picture captures my interest in both star formation, where new solar type stars are being formed at the edges of these pillars, and also these massive stars. And maybe something that people often don't realize is that low mass stars like the Sun, they are very long lived. They live for 10 billion years, whereas massive stars only live for a few million years. But the interesting thing is that the formation channel of low mass stars is very similar to the lifetime of massive stars. It's only a few million years. So if you look at star forming regions with massive stars, and they are only young, so they're only a couple of million years old, you will always have both. You have the massive stars that are short-lived anyway, and you have this early phase of the solar type stars. And that means that the two are related. And I think that's very interesting. Now, the first time I personally became aware of these kind of pillars was when I was an undergraduate student in Washington, DC in the US, and the Hubble Space Telescope had now been refurbished. And you saw these beautiful, these are really the original pillars of creation that were imaged in the mid-90s by Hubble Space Telescope. And the Washington Post opened, the big headline was, Hubble discovers heaven. And I was looking at this picture and I thought, yes, indeed, this is just amazing. I don't think I've ever seen a more beautiful picture than this one. And you basically see these pillars being eroded by the massive star that is lighting this up, and clearly there must have been material here before, but that's already been left. That's already been eroded, and these are a bit denser, and they're still left behind, and new stars are being formed. And I think this is amazing to see these kind of stellar nurseries. Now, my understanding is that this is the first beautiful picture like that, but obviously these were already known before Hubble. So I don't think Hubble discovered these pillars, but I think it really, brought these kind of pictures to the imagination of many, many people. They're basically very reminiscent of stalagmites in caves, and if you've ever been to Bryce Canyon in the United States or so, you will have seen structures like this. And I think they're just very, very interesting. And if you're wanting to know more about how these form, then actually you should talk to Jonathan Mackey from DIAS, because he has really worked on this in his previous life. So now I really want to come to something that I think is actually a massive breakthrough in our understanding of star formation. And that is really discovered by Hubble, the droplets in Orion. So Orion is a bit closer to us than these. This is one of the closest star-forming regions where massive stars are present, the Orion Nebula Cluster. And what you can see here are these protoplanetary disks. So you see really the photoevaporation, the material, the dusty material being lit up and leaving the system. And you see silhouettes of really what are supposed to be disks. The disks out of which planetary systems form, like our own solar system. We've always seen, of course, that planets are aligned in our own solar system, so that immediately suggests a disk. And angular physics of angular conservation of angular momentum tells you that when a star collapses, it should form a disk. But up to this point, disks had just not been seen. So this paper of 1993 by Odell et al. Is really, I think, the first discovery of protoplanetary disks, where really I think the Hubble Space Telescope made a massive impression that these protoplanetary disks, that stars really form with planets around them, and therefore it's not at all a surprise to later on find all these exoplanets, because we know all these stars have formed disks. We know planets formed out of them, so it's quite obvious that that is a typical way that stars form. And we now know also that the sun probably formed in an environment not dissimilar from this one, a cluster about the size of Orion. So here's a number of these droplets, and even a picture of a really beautiful one, which of course is an artist impression. But it is quite interesting that without Hubble we would not have seen these until actually only last year with ALMA, which is a very long wavelength observatory in Chile, where you can clearly see the disk of this Titori star, HL Tau, and you can really see that certain parts have been eaten up. Parts of the disk have been eaten up by planets, or at least that is very, very likely, because that is consistent with current dynamical models. But I think it's quite interesting to realize that the Hubble Space Telescope already discovered these kind of protoplanetary disks 30 years before ground-based observatories could do these kind of things. So to me, that is a massive discovery of Hubble, of the Hubble Space Telescope. Now we come to cosmology, because that is one of the reasons why Hubble was made. It was actually meant to measure the Hubble constant, and therefore cosmology has to feature in any talk about the science from Hubble. So many of you will be aware that we live in an expanding universe, and here you see a balloon being blown up and it has galaxies on its surface. That looks a bit ridiculous, but it's, I think, a very good analogy of what our universe really looks like. Basically, with time, you blow up the balloon, so the balloon gets larger and larger, and the surface of the balloon is two-dimensional, and we can only see it, of course, in 3 dimensions, but it's quite similar to our universe, where you just have one extra dimension, one extra spatial dimension, and the time direction is basically given by the blowing up of the balloon. And what you can see, if you have a galaxy, say this was our galaxy, this one here, then all these galaxies seem to be moving away from us if the balloon is blown up. So this galaxy seems to have a special preference. But many people thought that when all the galaxies were moving away, that we were special. But that is actually not true, because if you had not picked this galaxy, but you had to pick that one, say this one, and you look at the blowing up of the balloon, then those galaxies also move away. So it's became quite clear that the space itself in between the galaxies is increasing, and that can only be explained by an expanding universe. And if you have an expanding universe, that basically means if that is today and that was yesterday, and the day before yesterday it was even smaller, so that is where the idea of the Big Bang then also comes from, that you really came out of a singularity, basically just a point. And in the future, this balloon may grow and grow. Now, we knew there was an expanding universe before Hubble, don't get me wrong, but there's a lot to be discovered still, and I will come to that in a moment. Just to remind you all that if you have an expanding universe, that if you want to look back in time, you need to look far away. So the further away you look, the further back in time. And this is one of the massive projects undertaken by Hubble. It was the Hubble Deep Field, also in the mid-90s. So basically what people decided, what would be a great experiment, is to pick a dark patch of the sky. So you don't want to look in the galactic plane because there's too many stars there, but you go outside of the galactic plane and you pick a very dark patch, and now you just integrate for forever. And this was what was found. And I think this is just an amazing number of galaxies at all different distances. And a more recent the Hubble Ultra Deep Field has been taken maybe 10 years ago or so, where this was even followed up to redshifts, like distances even larger than in the original Hubble Deep Field. And you can learn a lot about how galaxies form, their shapes, and their distribution, and actually also by seeing at what wavelengths certain galaxies are visible and at what wavelength they drop out. You can learn about all kinds of dropout techniques of certain galaxy selections, and you can find out which ones were very early in the universe, especially with the second Hubble Deep Field. And basically, we have really learned that we are getting very close to the first galaxies. And I'm sure you've seen pictures like this before, where you have the Big Bang on the left, and then when you increase the size of the universe and you expand it, there is a very key phase in the life of a universe, which is called the epoch of reionization. This is where the first stars and first galaxies came to exist, and the first light appeared. And then billions of years later, we have galaxies like our own today, where we have stars forming and planets forming, etc. So basically, if we are sitting here in a galaxy on this side, if we want to learn about our origins, our real beginnings, we need to look back in time. And we now know that that is about 13.8 billion years. And that's actually remarkably precise, because some of you will probably over the years and over the decades have learned that the age of the universe was always varying. Sometimes it was 10 billion years, sometimes it was 20 billion years. So what is it? And why is this number always changing? Well, that is related to this other part of the Hubble Space Telescope to do with the Hubble constant. And I want to just remind you a little bit about what Hubble's idea was. Basically, what he knew was that there are Cepheid variables. So this is 100 years ago. Cepheid variables were massive stars, but not the kind of massive stars I'm talking about, but clearly stars more massive than the Sun, that are pulsating. And from their pulsations, so the fact that these stars change their radii on regular intervals, you see these sinusoidal periods, and you can measure those periods. And it turns out that those periods and those brightness variations have a very nice relationship. And that was already found by Henrietta Leavitt. So you have the magnitude, so the brightnesses versus the periods. And why is that so interesting? Well, this means you can find distances to galaxies far away, because if you have a cow very close to you, the cow looks very large. If you have a cow in the far distance, it looks very small, but obviously the size of the cow is similar. And the same with the light bulb. The light bulb at the back of your garden, it looks fainter, but it's obviously just because it's the back of the garden, and if it's the same wattage, the same power coming out as the light bulb in front of the garden, then by measuring the differences in these brightnesses, in these luminosities, you can learn about the distances. So that is one ingredient that went into Hubble's work, was to use this knowledge about galaxies, that they are at all kinds of different distances. And then the next ingredient was that he wanted to know how rapidly they were moving away from us, because it was already known that they were all moving away. And why do we know that galaxies move away from us? Because of their redshift. Now, many of you will be familiar with the Doppler effect. The Doppler effect can be applied to any waves in physics. It can be sound waves. So when an approaching train will make a certain tone, like whip, it will come higher, and then when the train moves away from you, it goes the other way around. So the same with light, of course. Anything moving towards you is shorter, is blue shifted, and anything that moves away from you is red shifted. Now, and I say blue and red shifted, how do you know? Because this is just a spectrum. This is a continuum spectrum. In the background, all these colors give you the optical continuum spectrum, going from blue to red, with yellow in between. But on top of that are lines. These are chemical elements that are in the spectrum of stars. And basically using those lines, we can actually learn which lines are blue shifted and red shifted. And that way we can learn about binaries. And that way we can also learn about galaxies moving away from us or towards us. And interestingly, if we had a universe that was static, you would expect on average to have as many galaxies moving towards you as away from you. But it turns out they're all moving away from us. So the only explanation is indeed that the universe is expanding. And I just wanted to say at this point, if people are unfamiliar with spectra, this is the optical spectrum. And earlier I mentioned that the ultraviolet was also a wavelength range that Hubble can observe in, and that is basically to the shorter wavelength than the blue. So you have the blue, the violet, and then the ultraviolet, and then further down you get X-rays and gamma rays. Whereas on the red side of the spectrum, if you go redder than red, you go infrared. And if you then go to even longer wavelengths, you go into the ALMA range, which you call the submillimeter range, and then the radio range, very long wavelengths. So the Hubble Space Telescope can take beautiful images, but it can also take the spectra against these continuum color distributions. So with photometry, you can learn about the continuum of these kind of, you can compare how much blue light there is compared to how much red light. But if you want to know the details of the movements of stars and galaxies, but also within stellar atmospheres, you want to know the details of the physics in the atmospheres, you really need to take spectra. And that is one of the interesting things we do in astronomy. So when Hubble had these data, he had basically the distances and the distances here and the velocities on the y-axis. This is the actual plot from that 1929 paper by Edwin Hubble. It is a clear relation. I mean, it's maybe not the best relation you've ever seen, but it's a clear linear relationship between velocity and distance, and that is where this HST Key Project came in, because there is this constant in cosmology called the Hubble constant, and the question. Because when I started to do astronomy, a lot of my physics peers were like saying, "Yeah, but astronomy is not a very precise science because the Hubble constant is not even known if it's 50 or 100, and 50 or 100 watt. It's actually kilometers per second per megaparsec, and a megaparsec, mega means a million, and a parsec means about 3 light years. It's a funny unit, but before the Hubble Space Telescope, it wasn't very clear what the Hubble constant was. And now we know with pretty good precision that the Hubble constant, thanks to these Cepheid measurements in nearby galaxies with the Hubble Space Telescope, these measurements of Hubble have been massively improved. And now we know it's 71. So it's not 42. After all, it's 71. And the error bar is very small. It's only 2 now. I mean, that becomes, even a physicist will have to take this stuff seriously now. So this is H naught, not to be confused with R naught. I was just thinking when I wrote this down. But basically, this is the Hubble constant, and I think this is a really precision measurement of a quantity that Hubble invented 100 years ago. So I think that's amazing that this is now established. And that also means that we now know the age of the universe very accurately, because the age of the universe is basically 1 over the Hubble constant. So if the Hubble constant is 50 or 100, then you have a factor 2 uncertainty in the age of the universe. But now you will probably have noticed that the age of the universe is pretty fixed now at 13.8 billion years. And that's not going to change very much, because this has now been set on a pretty firm footing. Yeah, I think that's a massive achievement, and that is therefore my personal second highlight. Now, obviously, I have to say, these are all just personal opinions about Hubble's achievements. The telescope has made advances, as I said, in literally every field of astronomy. So I'm sure I have forgotten some amazing other fields of astronomy. I cannot give a talk without not talking about these massive blue stars. So I will mention them. So this is not a massive blue star because they're far away and we cannot see their detail like we can see for the sun. This is a picture of the sun with a blue light. This is fake news. It is not real. But hopefully we will one day be able to image these kind of stars with the next generation of interferometers and other observations. So these massive stars, as I said, are blue. They're much brighter, but the key point is that they're hot. So in massive stars, we always make this joke when we have this spectral energy distribution. The problem with observing in the visible or even in the infrared is that we can only see a part of the spectral energy distribution. For physicists, you will be aware that is called the Rayleigh-Jeans tail of the spectral energy distribution. So the problem is that if you only observe massive stars in the visible, and you just look at the spectral energy distribution, you cannot know the nature of the beast. For that, you need to go to the ultraviolet, and then you will discover what the nature is. And this is a joke from Peter Contry from '86, but I think it's still very valid today. So what we really want to, what I think we can still make a massive improvement is by understanding these massive stars in the regime where they are actually producing most of their light, and that is the ultraviolet. So we have UV radiation, lots of it. So you wouldn't want to get a tan near a massive star because you would be, well, you'll be grilled. So what is ULLYSES? ULLYSES is the ultraviolet legacy library of young stars as essential standards. And this is not misspelled. The first thing you probably realize is that's crazy, the double L there, that's wrong. It is wrong, of course, but this is the legacy library. So this is the way they want to spell this. I didn't come up with this name. It's 500 orbits for massive stars and 500 orbits for these young Titori stars. And this ULLYSES project is the biggest project that HST has ever performed. So it's been going for 30 years, and now in the last couple of years, it's going to do the really interesting stuff, the massive stars. So a lot of progress had been made with the IAA, the precursor of Hubble, but the Hubble Space Telescope hasn't, well, there have been improvements in our understanding of massive stars, also thanks to some UV spectroscopy with Hubble, but not as much as we should. And I think that is where we're now going to make a big breakthrough in the next couple of years. So ULLYSES is setting sail. I have these beautiful images in the background because if you look at what it's actually going to do, is going to measure all these spectra. So you have all these wiggles here. And for a public talk, that is maybe not ideal. So that is why we have all these nice pictures, of course, like this 30th anniversary. But what we really want to know is the life cycle of massive stars. So basically, how are they going from this phase where they're young and where there are O stars, the most massive stars in the main sequence, and how do they make these Wolf-Rayet stars, and how do these Wolf-Rayet stars then collapse into black holes? And that is what we're really after, and we want to do that not in our own Milky Way, but in nearby galaxies. And the instrument we use for that is the Cosmic Origin Spectrograph, COS, on Hubble. So this is one of the latest, probably the latest new instrument on Hubble. So this was the last surface mission. This was installed, and it's extremely sensitive in the ultraviolet. So it can do a much better job than IAA did in the past. And we can really now take lots and lots of high quality spectra to learn a lot about stars in our nearby galaxies. So these are the large and the small Magellan and the Cloud. The interesting thing about these galaxies is that they are a bit more reminiscent of the early universe because they have a lower metallicity. They are more pristine than our own Milky Way. And in addition to these, we have some Pathfinder sort of observations also in Galaxy Sextans A and NGC 3109, which are even lower metallicity than of the SMC. The SMC is about 20%, the metallicity of the Milky Way, and these are only 10%, of order 10%. So we can really learn things about massive stars as a function of its age of the universe, basically. And in addition to all this, we are, as I said earlier, or was mentioned by Danny, I think, we are going to use ESO VLT ground-based observations with the X-Shooter telescope instrument on VLT, which will take optical and infrared spectroscopy in addition to the UV spectroscopy. So with this new X-Shooting ULLYSES project, we really want to get all the parameters and mass loss rates of all these massive stars to really learn about the evolution and the fate of these massive stars. Because you need to know the mass of a star that it has today, but also how much mass it loses with time, because then you know what its fate is, what is its final mass, and what is its black hole mass at the end. And very interesting for cosmologists is that we also provide all the ionizing fluxes of all these different massive stars, because they need to know this for their understanding of the reionization of the universe. And it's also important for local star formation, because if you want to understand star formation, as I said, you need to understand how the massive stars are photoevaporating disks, etc. So for cosmology, one of the big questions, of course, is this epoch of reionization. So the epoch where the first light appears, so the transition between the dark ages and the reconnaissance. And we can really help a lot, I think, with this information of these massive stars at low metallicity for people who want to study the very first stars. And in addition to that, it's going to be very important for stellar black holes. Especially these days with LIGO and Virgo, many new black hole masses have been found. And in the old days, when you had stellar mass black holes, these were always found from X-ray binaries. Like Cygnus X1 is probably the most famous one. It is a massive star with a 15 solar mass black hole around it, but 15 solar masses is the maximum mass of a black hole in our own Milky Way. But with LIGO, they're finding all these mergers of black holes with 20, 30, 40 solar masses. And even the record holder now, an 85 solar mass black hole and a 67 solar mass black hole, making a 150 solar mass intermediate mass black hole. We are really starting to probe the region in between normal stellar mass black holes and supermassive black holes in galaxies via these mergers. But a lot of people think that these 85 solar mass black holes are already impossible to form, but I have other ideas about that, and perhaps one day I can talk about that part of our research, because I think a lot of people are interested in black holes, I think, for good reasons. So I hope I have made you enthusiastic about the ULLYSES project and Hubble in general. And that was really what I wanted to show. So it's hopefully not just the pictures well, it's also the pictures, because the pictures are amazing, but I'm sure you've seen them before. But I hope that it gives you some ideas about other aspects of astronomy, and I'm happy to take questions.
Oh, thank you, Dr. Vink. That was certainly most interesting and nice. It was nice to see some of those pictures again. I haven't seen them for a while. I'm sure it's triggered a lot of other people's memories when they first saw, for example, the pillars in Hercules. It was certainly amazing. Terry has a couple of questions. Do you want to expand slightly on one of your questions, Terry, or?
It was very interesting what you were saying about the blue supergiants not going through the red supergiant phase, but collapsing directly into a black hole. What was sort of puzzling me is, since those stars are losing mass at a tremendous rate just through their nuclear burning, how is it that they can collapse to a black hole at the end of their lives when they're not when they're losing mass compared with what they were earlier? Did you hear that, Jorick?
Yeah, no, I hear you. I'm not quite sure where your problem lies. So because the stars are losing mass, they don't become red actually. So you basically already start removing the hydrogen envelope. So you have a stellar core and you have an envelope, hydrogen envelope, and because the hydrogen envelope is lost for the most massive stars because they are brighter and therefore they lose more mass also in a relative, both in an absolute but also in a relative sense than stars at somewhat lower masses. They remove the hydrogen envelope and therefore they stay blue. So they do expand a little bit, but they never make it to the red supergiant phase. They stay relatively compact.
Right.
And it's not that different from a 20 or 30 solar mass star. Their cores also collapse. No, the cores collapse, but then in the rebounds, of course, you get a supernova. But for these most massive stars, we don't think that's the case. We think they're compact enough that they will just collapse directly to black holes.
Yeah, well,
I must say that we haven't. This isn't completely proven yet.
Sorry, it's that phase that's puzzling me. They don't go through the supernova phase. So what is it that triggers the collapse?
They just run out of fuel. So it's
Right.
exactly the same. You basically, at the moment you have iron, you cannot get any more energy out of it. So you just come to a standstill, and that's why your core collapses. You no longer have the energy to support the gravity. It just falls in on itself, and the core collapses. But it doesn't quite expand all the other stuff out because it has stronger gravity and it's more compact, so it probably just collapses to a black hole. This is not entirely, I mean, we still don't know for sure. I mean, ultimately what we really need to know is have spectra of massive stars in different galaxies and actually just see them disappear without an explosion.
Right.
That will be the final proof that indeed the most massive stars directly collapse to a black hole.
Okay, thanks.
Andy, do you want to go ahead? Hello, Andy. Andy.
Sorry, Danny, just couldn't switch on my mic there. Sorry about that.
Okay.
Yeah, yes, sure. Just a quick question, probably totally irrelevant. But sometimes when you're looking at these protopleids and the formation of the solar system on a disk, there's jets associated with the disks. Is there or has there ever been any evidence of polar jets associated with the sun or its formation?
Well, we weren't there to witness it.
No, any remnants, but any.
Yeah, no, you're quite right. Jets are common.
Guns?
Sorry, jets. During the formation of stars, jets are common. We think they're most energetic early in the formation of the star, so not in the pre-main sequence phase, just a few, not like 1 million years before it reaches its hydrogen burning, but a few more million years before it. When they are not class 2, they're called class 2 young stellar objects, but more when they are class 1 or class 0 even young stellar objects. I don't know if you're familiar with that phenomenology, but basically when the stars form, they form from dust clouds, and you can only see them in the infrared.
Yes.
And then when they start to appear from the dust, that is when they have their strongest jets. The accretion rates are the highest. So the growth of the mass is the highest early on.
Okay.
And then it kind of levels off. By the time we start to see the protoplanetary disks, most of the accretion onto the star has already occurred, and therefore most of the jet activity has already passed.
Okay.
Okay. Yeah.
And that jet activity disappears, or I suppose my question is, what happens to the stuff that's coming out in the jets? Does it fall back onto the accretion disk, or does it just go off into the galaxy?
It just goes off into the star-forming region.
Okay.
And it's usually about, it depends on the efficiency, but we think it's maybe 10% of the mass or so gets lost in these jets.
Okay. Just a second question, if I might, Jorick.
Yeah.
Well, I've got you there. Just on galaxy formation. Now, I mean, you showed some images of the very early stages of galaxy formation. I was just reading recently there where they were talking about the globular clusters being central to galaxy formation. Is it, does that make any sense? I mean, okay, obviously the globular clusters cluster around the center of the galaxy, and that's how we detect the shape and structure of the galaxy. But I mean, the feeling seems to be that they're coming together. Apologies, that's my doorbell. The theory they were expounding was that the globular clusters themselves were a formative element of the galaxies. Does that make any sense?
I should really say this is really not my field of expertise.
Okay, it's not mine either. So
I would say galaxy formation and evolution is probably the area I kind of feel least confident about. It doesn't make complete. I don't know enough about this. I just don't know enough.
Okay.
I don't think I should say too much now.
No, I'll not push on it. Thank you very much for.
You don't mind if I jump in there, Andy, on that?
Sure, yeah, go ahead. Yeah.
John.
Certainly we know that some globulars are probably the nuclei of dwarf galaxies that have been shredded by our Milky Way, like M54, for example, and there's a suggestion Omega Centauri in the southern hemisphere, which is the richest globular we know that's circling our galaxy. That almost certainly could be a nucleus of a long shredded galaxy, and they've seen tidal tails from a couple of globulars. But in terms of them leading to galaxy formation, unlikely. More than likely, they're just left stranded, so to speak, when the galaxy collapsed to a disk.
Yeah, no, that makes sense, John. That's helpful. Yeah, thank you.
No, you're welcome.
Okay, Terry, do you have another query on the scope and its replacement?
Yeah, nobody knows exactly how long the HST is going to last, but it won't be indefinitely. And the JWST will have a largely different spectral coverage. What do you think we'll miss most whenever the HST is no longer working and we're relying only on the JWST for space imaging?
Yeah, I think it's almost certainly going to be the ultraviolet.
Yeah, but in terms of your research, will that sort of affect your studies of massive stars?
Yes, it would. It would. Now, I would still hope that that a new space telescope, or more multi-purpose type space telescope, will be considered. There are plans for. It used to be called the High Definition Space Telescope. Now it's called LUVOIR. It's a concept mission. But they're thinking about a 10, 12 meter type telescope, optical and UV capabilities.
Wow.
But obviously, these things are not cheap. So, and it will take a while, as we've seen with JWST. So even if these plans materialize, then it will take decades, I think, before we'll have it. So there might be a gap. But I think Hubble can still go for another. We don't know. it's been tremendously successful thanks to all these service missions. These instruments have been updated, so yeah, why not? Hopefully, we can keep going for another 10 years or so, or maybe longer even.
Well, I know it'll stay up there, but there's the problem of funding.
Yeah,
the maintaining of it and the ground station.
maintaining. Yeah, that's true.
Although a future service mission, say, and continued funding for a bit, I'm sure would be a lot cheaper than a brand new telescope.
Yeah, but at some point, I mean, IAA was still going after 20 years, and they just switched it off. I mean, at some point, I guess that it's a. You can, yes, it is relatively small cost to keep something going, but there's of course, if you also want to do new things, then you also need to do that and invest your money there. So it's the politics.
Fine line to be drawn.
You have to draw a line at some point. Look, I think it's absolutely fine if there is a gap. You know, for the massive stars, as I say, we can see a lot of the light in the ultraviolets, but we can do a lot with optical and so on as well. It's not as if everything is closing down on us. I mean, in many ways, things have been opening up because we no longer just have electromagnetic radiation, we now have gravitational waves as well. So we learn about the endpoints of massive stars. So where one door closes and only one door opens, you know.
Right, Jorick, great, thanks, it was fantastic.